already. So, welcome to three tips for better graphs and stats in science fair projects. Um, like I said before, this event is one that we cross promoted with the Minnesota Academy of Science. Liz, who you'll meet in just a second, Liz and I were talking and thinking about things we could do to benefit the groups of teachers that we work with in common. And we came up with this idea of hosting a science fair themed webinar. Um, and so I guess with that, Liz, if I could turn it over to you to do a little bit of introduction.
Yes. So, hi everyone. My name is Liz Blumen. I hope you can hear me okay. They're not blasting the music too loud in this beautiful coffee shop. But I will introduce myself. I'm Liz Blumen. I'm the Director of Events and Outreach at the Minnesota Academy of Science. We're really happy to be here promoting this webinar with DataClassroom. I've had the lucky chance to meet Aaron on a couple different occasions, and we've talked about how great his program is great for science fair. So I run the state science fair in the state of Minnesota, and I'm just really looking forward to hearing about these tools. We'll be hosting the state science fair for anyone in Minnesota on March 28th at the River Center in downtown St. Paul. Um, and I'm available for questions if anyone has any at the end.
Okay, great. Well, thanks, Liz. And I'm Aaron Reedy, co-founder of DataClassroom. I was formerly a high school science teacher in the Chicago Public Schools, and really got interested in helping kids do better work with data when I was a graduate student at the University of Virginia. Um, and I will say, when I was a classroom teacher, I was not a participant in science fair. I was really unaware of just the amazing community and the amazing work that students do through science fair. It was really only in my work with Data Classroom that I've gotten to meet so many of you out in the science fair community, because you all were pretty early adopters of our tools. You had acute needs for students learning to work with data, as that's kind of an integral component of the science fair experience. And you all have been very vocal, and I really appreciate that. And a lot of just wonderful additions we've made to Data Classroom over the last 3 years were the direct result of you all, and you all asking me for things that were really smart. And so there's been many changes that have been made to Data Classroom because of that. So um, the title of this webinar was three tips for better graphs and stats in science fair projects, but I'm going to give you my list of 6 top tips, and then the webinar is going to focus on three. So these are the three that we're really going to focus on. These teach students to collect tidy data, um, the make intentional graphs, and use stats to put confidence to conclusions. These are the three that we're going to focus on. But when I was kind of, as an exercise, preparing for this kind of a presentation, I also think I have a few more tips, and we might have to do a part two to this webinar at some point in the future. But begin with the end in mind, I think, is really important. The more planning you can do with your students up front, or the more planning your students can do up front, the better project they're going to produce. And then focus, make your questions small. As I work with science fair kids around the country, I often see just, wonderful, ambitious questions, but they're sometimes just far too big to do in one project. There's just no way to collect enough data to answer that question, in a single year, and certainly not in a single science fair project. And then the last tip is to make the judges feel smart. And this is a variation of tips that I've given to young PhD students when they're writing their first papers for publication, is that you want to make the reviewers feel smart. You don't want to ever make them confused or kind of scratching their head and not understanding what it is you're trying to tell them. The same thing goes for science fair judges. When you're a student presenting your project, you want students to easily grasp what you did, even if it's quite complex. You want to say it in very straightforward way, and you should be able to explain it without using a ton of technical jargon. So these are kind of my six, but like I said, we're going to focus on the first three tips: the teach students to collect tidy data, make intentional graphs, and use stats to put confidence to conclusions. Um, and over the next 40 minutes or so that we have remaining, we're going to cover these things. Um, So these three that are highlighted here. So number one, teach students to collect tidy data. Um, this can take a little work, and I'll say that um, much to my surprise, this doesn't really happen by accident, and I'm not surprised by that anymore. But I was surprised by that at first when I started working with science fair kids, and I was surprised by what a tremendous lift it can be to teach kids to make a tidy data table, and how hard it can be to do analyses when the data are not in tidy format. I've often heard data scientists say that they spend more than 80% of their time just cleaning up other people's data sheets before they can analyze them. And I think there's a lesson in there in that it is a lot of work to sort of reformat a data sheet or reshape it. And so I think it's really important to teach students from the outset that when they set out to collect their science fair data, organizing it in tidy fashion is going to help. And now tidy data, it has some specific conventions. And if you've been on a data classroom webinar before, or if you've been to a few of them, I'm guessing you've heard us touch on this, because this is something we bring up a lot because it's something we see students struggle with a lot. But the basic rules of tidy data are that each variable gets its own column and exactly one column. So we don't want to split one variable into multiple columns. And in this example, you can see the variables that we have are country, year, cases, population. And every time we make an observation of those variables, we add a row to the data set. Oftentimes, tidy data can be called long data or long format data, um, because as you collect more data, your data sets get longer, they don't get wider. The width of the data set is determined by the variables that you have and that you're measuring and that you're recording. But the length of the data set is determined by how many observations you make or how much replication you're doing. And so the data set gets longer as you collect data. And then we refer to the data that are being collected as values. And this is true whether we are talking about data that is categorical. And so, like, an example of that here is country. You can see we've got Afghanistan, Brazil, China. Those are all values of the variable called country. And then for numbers, I think it makes much more sense. If we're talking about, height in centimeters and you say, 167, that we're used to thinking that of that as a value. So, but I also just want to point out that it will take some explaining and some explicit modeling for students to get this vocabulary so that they can understand that, when we talk about a variable that's categorical, that has values, whether it's, red, yellow, blue, male, female, other, country, what Afghanistan, Brazil, China, whatever we're talking about, those are values of a categorical variable. And this is a really common example of what we might see as untidy data. And it's not to say that this data is bad. I sometimes kind of shy away from messy. Sometimes people like to call it messy data, but messy has a lot of value judgment attached to it. And it's really just any data that's in any format that doesn't follow those rules of tidy data. And so here you can see that the columns we have listed that this student has made is they have day, and then those are filled in with numbers 1 to 5, which are the values of day. And then they have plant A and plant B as two other columns. and then they have numbers written in there. And this also presents one of the issues with untidy data is that oftentimes it will leave out the units. So we don't know what those numbers represent. We also don't really know what they're measuring. Plant A and plant B are not very specific. In this case, the student was actually measuring height of the plants of little seedlings, and um, you can see that reformatted in a tidy format like this, we have one category to represent each of the variables, and the three variables we have here are day, plant, and height. And we have 10 observations in total. So the data set has 10 rows. And you can see the one that is probably the least intuitive to the students is writing in the values for the variable called plant. It's much more common at first to see something like we see in the upper example, where they'll just jot down plant A, plant B, and then they'll start recording heights in those columns. But if we really want to think about experimental design and ask questions like, what is your independent variable? What is your dependent variable? If we organize data by variables, it's much easier to do. And in this case, we can see that, our dependent variable is height, and we can also point to a column that carries all of the data for that, that dependent variable. In this experiment, I guess maybe, or from what we can see here, I guess maybe the independent variable is plant. Which plant is it? It's A or B. Um, but we don't know if maybe they were in two different treatments or something like that. But we don't know. But this is just kind of a basic illustration of untidy data made into tidy data with a very simple kind of toy data set. I'll also say I'm not really demoing it on this webinar, but within DataClassroom, we have a melt function. And if you look it up in the user guide, and maybe if we have time at the end, I can show that. But if you had the data set on top, you could just melt it into this data set on the bottom with just a couple of clicks, and it would convert to that format. Melting your data won't fix every sort of untidy issue, but when you have this issue of one variable that you've actually represented across multiple columns, and then you also have an unnamed variable, you can fix that with the melt function in DataClassroom. Okay, so um, let me back up just a second. I got Zoom windows covering up stuff there. Go back. So tip number two is make intentional graphs, and this one we're going to spend a little bit more time on. This is really key, and one that I would say gets overlooked a lot. I've been to see the posters at the International Science and Engineering Fair, and just about every single one of the projects that makes it to that level of science fair is really fantastic. But I will say that not every one of the graphs that makes it to that level of competition is what I would consider a top-notch graph. And the same goes for published science. You will see some absolutely beautiful works of data visualization if you look through a recent scientific journal, but you will also see some just kind of average ones as well. And I think the difference is how intentional you are when you're going to communicate your data. And so as an example, within DataClassroom, I tried to make what I would call a default graph. And I put a little asterisk by it because um I had to dull it a little bit, I guess, is for lack of a better word, because the defaults in DataClassroom aim to be a little bit better than your average default in other stats or graphing programs. But so I tried to make this as close to sort of a universal default. Um, in DataClassroom, when graphing numeric data, you'll see a jittered dot plot like you see here if you're comparing two categories. That graph type is maybe not that common as a default. I think maybe much more common you would see like a bar where the height represents just the average with no variance or something like that. But um, this is what we're using as the sort of default for this example. And this example on the right is the exact same data. But this is a graph that has been made much more intentionally. There's been a lot more intentional decisions that go into the graph. And you could do great science and represent it with either of these graphs, and you could have a very wonderful science fair project and represent it with either of these graphs. But when it comes time to have your science judged oftentimes rather quickly in a science fair environment, I think the graph on the right just helps you put the best foot forward with your data. It just makes it easier to kind of more quickly grasp what the main result is. And I'm going to break this down and go through, what are all the differences that go it from, getting you the graph on the left to getting you the graph on the right. And if anyone has any questions, comments at any time, um, Liz and I are kind of keeping an eye on the chat, so feel free to just jump in and fire away with any questions or comments that you have as I do this. So, some things to consider before I break down the creation of that graph. Um, Things you can consider: color and transparency of dots or bars or lines, the size of data points and bars, the dimensions of your graph. Are you making a very square graph, or are you making a very rectangular graph? You can emphasize different things in the result by doing that, although it won't change the data, but it can change how easy it is to see whatever trend or result you're trying to highlight. Think about font sizes and largely make them readable and larger than you think they need to be, because you never know, who's going to be judging your poster. We all bring a different range of visual acuity to when we're looking at science, and you want to make it very, very easy to read anything on the graph. Um, you can change the shape of the graph. That's really similar to the dimensions. Also, if you're showing replicated numeric measurements, you want to add some visuals to highlight the central tendency, whether that's a median or a mean, and you also want to show variance in some way. You never ever ever want to show a measure of central tendency like a mean or a median without giving some indication of the variance that underlies it in the data set. And so, this can be done in a variety of ways. It can be done with like box plots. It can be done with error bars. It can also be done by showing the raw data aside or next to or on top of your measures of central tendency. So those are very important things to do. You can think about adding connecting lines if it's like time series data, or regression lines if you want to show a trend or some kind of model that fits your data. And then also clear access labels and titles. And I think you should really work hard to avoid using jargon in your access labels if at all possible. Sometimes you can't get around it if you've got, say you're showing gene expression data and you have a gene that you need to label, and maybe that's the best you can do. But sometimes you can re sort of word the titles of different groups or sites or something, just to make them a little bit more accessible to a lay audience, or to anyone who's viewing your science fair work. Okay, so let's break down um, some intentional graph design here. So this was our example of an intentional graph, and we saw the default graph, and then we saw this. But I want to point out all of the specific choices that were made in producing this. So, um, first thing, we chose a complementary color scheme with the dark blue and the light blue, and it just makes it look nice, and having visual appeal is nice to have. And I think it there's research out there that shows that it helps people perceive your work better. But the other thing it does is it can emphasize that we have two groups, right? So we have two different colors, one dark, one light. It reinforces right away that we have two different groups. Um, Second thing we did, we enlarged the data points. We increased those. The default points were much smaller, and that allows us to kind of show off that sample size that we have. And if you're a science fair research student who collected a lot of data, you don't want to hide that by just showing an average. Like you want the judges to right away see that, you collected a lot of data, you have a lot of replication. So any conclusions you have, you can be very confident in those. Um, we removed the grid lines from the graph to get a cleaner look. That's overwhelmingly the style that you will see in scientific publications. It's not strictly a requirement, and there might be situations where you feel like the grid lines actually enhance something that you want to point out. But in a lot of cases, I think removing them is the way to go. Um, we also made the graph instead of as a horizontal rectangle, which was what the default our program was giving us, we made it as a vertical rectangle. And we did that because the difference between these two groups shows up as a difference in the vertical height between the bars. So when we make that graph a vertical rectangle, it stretches that out physical distance on the figure, and it emphasizes that result a little bit more. Now, it doesn't change the scale. The means of those two groups are still at the exact same values, but it makes that difference emphasized there. Um, we increased the size of the axis labels quite a bit over the default. We want them to be easily readable at, say 7 or 8 feet away from a science fair poster. So we increased those pretty much as big as they would go in this case. So those are quite a bit bigger. Um, we added the bars to highlight the means. So if we want to make a point that these two groups are different, one of the ways we might characterize that is by reporting the averages of the two groups. And so we added bars to show that. You can also do that with like a big dot with error bars, but we did it here with these bars. Um, and then we always want to accompany uh, any bar that shows a measure of central tendency with error bars to show this variance. So we're not hiding from the variance. And here we're actually showing the variance in two ways. We're showing it quite literally by showing where all the data points are, but we're also showing it with those error bars there as well. We also made the points transparent so that we can see when we have overlapping points, and you can see the areas where we have a lot of points on top of one another get a little bit darker. And so that was a conscious choice to make those uh, transparent. We enlarged the X and Y markers. So this is like the sheltered and exposed, and then the numbers 0, 1, 2, 3, 4. We made those larger just like we did with the axis labels. Um, we also included a caption. Whenever you have error bars, you need to say what those error bars are, because there's lots of choices you have with error bars. They could be standard error of the mean. They could be two standard errors of the mean. They could be 95% confidence intervals. They could be standard deviation, and they mean different things. So you always want to include some kind of, caption. It can be fine print, but you want to include what those error bars are representing. And then I chose a variable names on the graph I chose for understanding. And so like we called these two groups, we called this habitat, and the values are sheltered and exposed. This might have been some other name, it might have been like uh I don't know, research sites in northern Canada on the Atlantic coast or something. You might have had a messier name in your actual data set when you were recording the data, but when you go to your presentation graph, you want to choose something, nice and simple that your average person is going to be able to just grasp. Okay, I know what they're talking about here. So all these purple arrows are showing, each one of these things was a choice that went into this graph making. And I'm just gonna jump over to DataClassroom for a brief second and actually just kind of go through this process of to show you kind of how you would do this in graph making, specifically how you do it in Data Classroom, but also just to show you that you're going to need to make conscious choices and the kind of thing that you would do to create that. So let me just pull that up again, and I will share my screen once
Sì,
again.
accidente. Mm,
Sorry, do we have a question,
Giusto.
or is this, I think, just an inadvertent unmute there? Um, so uh, here we have the sort of the kind of what I called the default graph, and I just want to go through some steps to kind of make this into something closer to the graph that we showed as kind of an exemplar of intentional graph design. So to do this in Data Classroom, you would open up the appearance menu. Lots of graphing and stats programs have their own version of an appearance menu, but you're gonna play with these settings. So things that we might do, I might increase the size of the data points. One thing I didn't list this when I was going over what I did. I took off the edges around the points to give them a softer look, and that when I make them transparent, that also kind of helps them fade into the background there as well. I went and I chose to show the mean as a bar, and instead of positioning it off to the left, I put it to the center. Um, and let me go ahead and make those changes for a second. So if I go ahead and I add descriptive statistics, now we can see we've got those bars on there. One other thing, I turned down the jitter on those points so that they would compress a little bit and fall within the borders of the bars. I'm going to go back into the appearance menu again and make a couple more changes. One thing I'm going to do is I'm going to take away those grid lines. And I think that a time to do that is when you've got a visually busy graph, like if we're choosing to show all of those data points on there, that adds a lot to it visually. So I'm going to go ahead and take those grid lines away. I'm going to also increase the axis labels quite a bit. So it was down here on this default that was 20. I think the actual default in Data Classroom is larger than that. But I had kind of intentionally stopped that down. So I'm just cranking it way up there. And we'll go with that's maxed out at 50. I'm also going to increase the Y marker and the X marker a bit. Those are the numbers on the Y axis and the labels on the X axis. So we're gonna increase those a bit more. So we'll get those quite a bit bigger. And then I'm going to close this, and I'm going to make one other change with the color of the data points for each group. And because these are both two different values of habitat, I'm going to go up to this values button right here. You can see me hover, and I'm going to choose uh maybe for sheltered, I'm going to choose a custom color. We can go with that, we can keep that kind of dark blue scheme, but I'm going to turn up the transparency on that. And then for the exposed, I'll pick something complementary. So I'll pick, a much lighter blue, and I will also make a custom version of it where I turn up the transparency on that. And actually looking at that blue is just way too similar to the first one. So I'm going to choose more of a teal, um, and then do that. And so now we're getting closer to that intentional graph. And then finally, that other thing that I did was change the dimensions of the graph. Um, some graph programs that you can use for publication quality stuff will allow you to do that. Data Classroom will allow you to do that if you change the dimensions of your window. So like there, I couldn't go any smaller than that. So I'm going to go to about there. And then I'm going to also change this by clicking on this button up here to hide the variables up at the top of the screen
We had a
Dude,
question, Erin, in the chat.
yeah, go for it.
The question was, could you use contrasting colors or opposite colors?
Yeah, you probably could. And this, I think this gets into a real um subtle thing. I think it's there's a huge benefit you get right away when just choosing different colors for groups. And that benefit is compounded when you have multiple figures on a graph and you use the same color scheme in all of them. Because if we're going to compare sheltered and exposed habitats by some other measure and we have a second figure, using that same color scheme helps. Now, specifically the question about using, contrasting colors, like say maybe opposite colors on a color wheel, that's fine. You'll get maximum contrast with that. I would say the thing to do is, kind of look at your overall poster that you're presenting and say, how does this fit in? Is this pleasing to look at? And also, am I rapidly able to discern between, two groups? So you definitely wouldn't want two colors that were too close to each other. Whether or not you go to completely opposite colors on the color wheel, that probably depends on how it looks with the look of the whole poster, in my opinion. Good question. Yeah, so that's basically the process, but just really wanting to reiterate if you've got a student who's taken the time to do really great scientific research and they're going to present it, um, I really do think it's worth the time to go through the an intentional process um, of graph design. So I'm just going to go back to um, my slideshow now and making my way um, back there. A second. So we went through this whole process and we can see all of the choices that go into that. I'll just wanted to show a couple examples of just how different graphs can look. So you can just see them side by side and realize like what a big difference that intentional graph making can make, in your presentation. And so you can see here on the left, that's kind of like the default settings. The graph on the right, we've made all sorts of changes with color and point size. In this case, we've gone with really small data points because we have a ton of data there. And the sample size really gets lost in the figure on the left. You can't fully appreciate just how much data is there. But with the graph on the right with the small points, you can see really how much data are there. You also see the choice to color code them based on another variable. And so if that's, part of your story, in this case, we're comparing those latitude zones, you'll want to make that, visible in the graph. So that one I think is a good example. This is another example where we've got kind of the basic default graph on the left, and the graph on the right. There's a couple of things that are different about it. The biggest difference is we've just chosen a different graph type entirely. Instead of just a standard bar graph or frequency bar chart, we've gone with this stacked bar chart, and it's really good for looking at sort of diversity between these groups. So all of the mineral lick that is arrayed on X, those that each represents a different group, and you can really see which groups are similar and which groups are different based on which of those bars kind of look similar or look different. And it's a lot harder to pull out that information on the figure at the left. At least it's harder to pull it out quickly. Another change that's made in this one is the titles. Like on the left, it was lick, and it's part of the biology of this. This was research conducted in the Peruvian Amazon, where they were looking at these naturally occurring mineral licks. And I'm sure that the scientists who did this research, that if you just said lick C, lick D, lick E, they would know exactly what you're talking about. But if you have to explain to a viewer, we were looking at these mineral licks in the Peruvian Amazon, then you probably benefit by using the two-word phrase mineral lick to help them understand what you're talking about. Um, and this, this one, again, this is data from just kind of a common lab that I see in middle and high school a lot. This is the potato osmosis lab. The graph on the left, it's technically fine. It has all of the data present into those different category treatments of molarity there. But the graph on the right really emphasizes that those are separate groups, and it's displaying the median and the box and whisker for each of those groups. So it helps you to, more readily make a comparison between those groups. It's maybe not a perfect graph, but it's by doing it intentionally, it helps get across that message that you're going for. So, and then the last item, and I am aware that we're getting close to the top of the next hour and running out of time here. So, I want to make this last point that to be competitive in science fair, I think you want to use stats to put confidence to conclusions. I've heard many science fair directors and science fair mentors use the phrase "stats get you to state." And while I actually think it's good projects and well-designed experiments that get you to state, I think stats also help get you to state. And so what I would think is a good approach for science fair students, and one that I've used in mentoring a number of kids, is you want to form your conclusions from your graphs before you use statistics. And I think often for a kid using statistics for the first time, it's just hard to make meaning out of pure statistics. But I think when you use graphs first and use it as a scaffolding for statistics, it makes a lot more sense. So just want to kind of show an example of how I would have a student do that. This graph that you're looking at, this is a simple graph, and it supports the conclusion that barefoot runners have a higher running cadence as measured in that steps per minute, SPM. And so you can see the barefoot in orange and the shod runners, the runners wearing shoes, in gray. And you can see that there's a lot of overlap in those two groups, but it looks like overall the cloud of points is higher for the barefoot runner. So your kind of typical barefoot runner would have a higher running cadence. And you can draw that conclusion just from that figure. You don't have to have statistics to do that. I would say the next step is to have students add what I call kind of pre-statistical thinking to their graph. And so what they've added is the average and 95% confidence interval. And they've displayed that with a dot off to the left of each of their raw data points. And so they can see, that average for the shod treatment is down, between 150 and 160. And the average for the barefoot treatment is up between 160 and 170, but closer to 170. And they can use the values of those means, 167 versus 154, to emphasize their conclusion, to help, kind of add evidence or to better communicate their conclusion. And then finally, if they go on to inferential statistics, well, they've already made the graph and they've framed the question. And this is a t-test graph. And this leads directly to a t-test within DataClassroom. When students make graphs, it'll help guide them to the t-test. But this is sort of mimicking the thinking. If you're an expert, will look at a graph like this and can right away tell that, hey, this is a t-test question. And so if students have already made their graph, they've gotten a leg up on that. But the other thing is, if they do their graph first, they really get that the stats are a way to express confidence in the conclusion with probability. They're not revealing a conclusion that we didn't already know, but they're showing us, how confident we are. When they see a small p-value, like in this case, it's p is less than 0.01, this is another way of describing this conclusion of saying, yeah, the barefoot runners have a higher running cadence, and there is less than a 1% chance of getting a difference between groups like this due to random chance alone. So they're able to, kind of communicate that result, and the stats become an extension of what they were looking at visually, to begin with. And this, it, I often say that, questions lead to graphs. And then I always like to add on to that is that graphs lead to statistics. And so this is a graph choice chart, which appeared in a journal called The Science Teacher. It was research done by the University of Maine. And I think it's a great starting point, and you can extend that to thinking about different question types, and that's what we have pictured in that white box that we've taken from Data Classroom's Graph Wizard. And you can see how those questions lead to different graphs, and those graphs have different subsets of statistical tests that will go with those kinds of graphs. And you can't, if we're looking at like the very far left, we're looking at those pie charts or we're looking at those bar graphs. We can't do a t-test with data like that. It just won't work. Those are graphs that are showing something that's categorical, and they're telling us, how many times we observe things in those different categories. There is simply no way to do a t-test with data like that. But the data we were looking at, where we had a number, we were comparing groups, that is a good fit. So I think, helping explain to students that first you should think about what your question is, then think about what your graph is. And if you've done all of that well, it will be easy to, track down what kind of statistical test you will need to fit that situation, no matter what resource you're using to do your statistics. So with that, we are about out of time. I will send out the slides to everyone who registered for the webinar. So you will all get copies of that. And then, yeah, Janet in the chat, I see asked, do you have a digital version of the Sci-Teacher chart and the article? Yes, those will be coming in the slides. So you can have those slides. You can even use them in class with students. I think they would be a good illustration for a group, going to get prepped for science fair. Digital versions of some of that stuff also exists within Data Classroom. When you start graphing and you go to stats, there's some variations in there. Also want to say, if you are from Minnesota and you have questions about Minnesota State Science Fair, you can contact Liz, and you see her email in white there underneath the contact information. If you have questions about really anything else related to Data Classroom in your science fair, Data Classroom in your school district, you can contact me. My email is in the hard to read blue on purple link there, but it's aaron@dataclassroom.com. Happy to take any questions that you have. And also, I want to say to Liz and the Minnesota Academy of Sciences, thank you for co-promoting us with this and co-hosting. It was great to do this, and hopefully helped some teachers who need it for science fair, and it'll come in handy this year.
Yeah, I'm really happy. I'm glad you brought up this opportunity, and I'm hoping more people will watch the virtual version as well, the recorded version, because I think it's just a really great tool to help teachers and students visualize their data more effectively. So I appreciate you. Thanks, Aaron.
Yep. Thanks, Liz. All right. And I'll say good night to the rest of you. And I'll stop the recording, but I'm also happy to hang out a little bit if anyone has a question.